So, why look at these solutions? Well, as you might be able to predict by looking at some of these, we may have seen these terms before, like potassium dichromate. Okay, potassium dichromate or even lead nitrate are things that have shown up in our labs. We've had those substances and we allowed them to react with other substances. Okay, but those reactions, when we took those substances, weren't in the solid phase, they were in solutions. Well, those solutions now change concentration, and depending on our concentrations, we could get weird results based off of the solubility curves. So we need to be able to understand how much compound is actually dissolved in those solutions. And that's where this is going to become extra fun for you, and that was sarcastic because we're now looking at more conversions. So I've got this chemical reaction. You should be able to tell me what kind of chemical reaction occurred. So yes, you should take a second to think about it. We've got that pause button. Okay, this chemical reaction is a double replacement. Okay, how do we know that? Well, what we're trying to do is identify the pieces that we see within it. We've got metals and we have nonmetals. So that's already starting to fall into that pattern. If we look at our products, the products also show that same pattern. Okay, so for sure we're looking at a double replacement. Okay, so now I want to push this further and say, well, how am I going to quantify this? So on a quantification, I'm going to have to run a measurement. Okay, and in this case, I'm asking an easier question. Let's take a look at our silver bromide. So the silver bromide, we've got, in theory, a multiple choice question here. Which ones are silver bromide? AgBr. I want to be able to quantify that. Okay, so if I was to measure the silver bromide, what device would I use to measure? Okay, and so what that question is asking: mass, volume, time, and length, right? Those were our core measurement systems. If we had mass, we could then do a balance. If we had volume, we could do a graduated cylinder, which is way too many letters, but oh my goodness. And of course, too many letters means I'll spell it wrong. Time, we could use a clock, and length, we could use a ruler. Okay, well, when do we use each of those things? Well, a balance is useful for when measuring solids. Okay, it can still measure other things, but the solids tends to be the easiest. Volume is great for liquids. Okay, a clock is time, so we're not really measuring solids, liquids, or gases. And a ruler is measuring the length or size of something. So again, that doesn't make sense for our individual phases either. Okay, so those don't work to measure our phases. They would measure changes in our phases, okay, be it their size or them appearing or disappearing. Okay, so if we go back and use that information with our equation, okay, the silver bromide, I'm going to throw gases in there under volume. They're usually easier to measure in volume. Silver bromide is which phase? Well, as we've discussed, that parenthetical with the solid, or the S, means solid, which means the best thing to use to measure this would be a balance. Okay, so nice and straightforward. We can use a balance to weigh that out, and we now know how much silver bromide we produced. Okay, so then the next question, where did it come from? Well, this is hopefully an easy question. This is why we have a chemical reaction. That silver bromide came when I mixed these two things together. Okay, when I mixed the aluminum bromide and the silver nitrate together, that then produced a reaction where silver bromide formed. And that's how I could then weigh the silver bromide. Well, if we're looking at this from the chemist's point of view, let's say silver bromide is an exceptionally useful thing. Okay, I want to know how much I can make before I start making it. Because if I start making it and it makes thousands of tons of silver bromide, well, that's probably something I don't want to make in my house because it could kill me in the house. Okay. But if it only makes gram amounts, maybe that's something that's easy for me to do inside my house and I don't need a lab. Okay. So the scale of these things becomes important. So I want to know theoretically if I start with X and Y amounts, and we'll address the amounts here in a second, of the aluminum bromide, how much silver bromide could I make? Okay, so you should already be thinking, well, dang, that's going to require a conversion, and yes, it will. So this is where we're going to bring back our conversion aspects. But it's going to become a little bit trickier. And the reason it's going to become trickier is that when we look at those conversions, the chemical equation allows me to relate silver bromide moles to moles of aluminum bromide. Okay, and in this case that would be 3 and 1. So the equation sets me up with these moles. But as we just addressed, if I'm going to measure this, I need a balance. I would be needing grams. So I'm going to have to do a mole to gram conversion, okay, as we discussed in our past videos. Okay, but now we bring in the next thing. How am I going to measure the aluminum bromide? Well, the aluminum bromide has this aqueous thing next to it. So if I went through to measure out on a balance to get a mass so that I could also do a mole to gram relationship, I'm going to run into an issue. The mass that I'm now obtaining is not of aluminum bromide. Okay, and you might be a little, but it's still aluminum. It is, but it's aqueous. Aqueous meant dissolved in water. If it's dissolved in water, we now have a problem. Because when I go through to take that balance or take that weight, the mass that I'm going to get is both water and aluminum bromide. Water isn't doing any chemistry here. It's not showing up in my conversion factor coming from the chemical equation. Okay? The only thing that I need access to is the aluminum bromide. But if it's already dissolved in water, how do I pull that information out? Well, I'd have to be given more information about it. The information that I would need would be a concentration of the solution. Okay. Well, what is concentration? Okay, depending on your age, you may have heard reference to something like ABV. Okay, ABV is alcohol by volume. Okay, that is a concentration. Okay, you could have seen other things. Our concentration is really just relating the amount, okay, of one substance to the volume of our solvent. Okay, and that should be a nice big tip-off here that we're generating a conversion factor. We've got an amount over a volume. We're looking at two units and their relationship. And that's exactly what we're going to do here. Okay, so we're now addressing concentrations and what units we should be using for concentration. Okay, so let's think about this as far as a chemist would go. Okay, what unit do I want to use? Because as we already see here, we've got one. We could use alcohol by volume. Okay, we could use the mass per volume of the solvent. Okay, that one becomes tricky because that starts to look an awful lot like density, right? And we don't want density here. We're talking about the mass of a solute dissolved in the solution. So mass per volume actually may be a horrible idea because that could easily be confused with that formula that you were told to not memorize for the record for density. Okay, so we don't want mass per volume. We for sure need some kind of volume measurement because we're looking at water, and water was a liquid. And then we need some kind of amount measurement. Okay, and we just said that mass was a bad idea. So what other amount measurements do we have? We have a counting measurement. We have that counting measurement of moles. Okay, why is that going to be a useful one to measure. We'll go back up to our chemical equation and look at the stuff we've already addressed. Okay? We've got moles per gram. We've got moles per mole. Okay? Moles shows up again and again and again when we're dealing with our chemical equations. So if I'm going to look at a concentration as a chemist, it probably makes sense that the concentration I want to show is the relationship between the moles of my solute and the volume of my liquid. Okay? And that is indeed what we ended up picking, which we'll see here in just a second with a deletion of everything. So if you want to write it down, now's the time to do so. And we end up with a new concept, so don't stress about the words yet. Okay? And we have a concentration, and that concentration is defined as moles of a substance per liter of solution. That substance can be a solid, liquid, gas. Okay? So moles of any substance dissolved in a solution. It is most commonly water when we're talking about Gen Chem because we want to minimize your toxic exposures. Okay? But it could be any real liquid. Okay? I now have a concentration. If I use the term concentration, that could easily be confused with, like we said, ABV. Okay? And I don't want it to be confused with that, so I want to be a little bit more specific in my concentration reference, and that's where I define that this relationship between moles and liters of a solution is known as molarity. Okay? Shown as a capital M. Just to add a little insult to injury, we're not going to use this, so don't worry about writing this down. If you move into 151, you'll see it there. We could also have referenced it as a mass of substance per liter of our solution. Note that the mass we're using as a unit is kilograms. Why kilograms? Because that gets us out of the gram measurement, which could get us confused with density. Okay? This is also just as equal a concentration. We would use it in slightly different situations. This unit or measurement or concentration, conversion is known as molality. Okay, for those of you being like, that sounds awfully similar to molarity, it was intentionally picked so that people would recognize that they were equally valuable. That's just dumb, but that's why we picked molality as a term. Molality tends to show up in a lot more places. For instance, if you've ever lived in cold environments, salt concentrations for de-icing roads are typically referenced in molalities because you're looking at someone monitoring the concentration of salt on the road, and that's easiest to measure in kilograms. They aren't doing a conversion of a substance, they're just trying to get rid of ice. Okay? And because their use is different, they change the concentration unit that they're referencing. Okay? So it is very system dependent, if you will. So we now have this new concept of molarity. The next thing you might be going as an aha moment, in fact, I'm fairly certain a few of you might be doing this, is that if we looked at our bottles that we've been using in lab, because a couple people asked me about it in lab, they're like, why does it say 0.1 M? What is that M? Guess what that M is? It's the molarity. That molarity is now referencing the concentration of that substance that was in that solution. So, for instance, that was very commonly found associated with 0.1 M AgNO3. Okay? What we were saying by saying that is there are 0.1 moles of silver nitrate in 1 liter of that solution. Okay? That's what it meant. Okay? Which is going to get to an interesting statement. When we write it out on the bottle, we just wrote 0.1 capital M AgNO3. Okay, why did we not write out moles per liter? Well, moles per liter takes more effort. It also shows a fraction, both of which are challenging things for people to deal with, and so we emotionally have stepped back from showing that, and we simplify it out so that we only see the M, okay, that capital M, okay? While we may be able to do that as chemists that have learned and understood the meaning behind these terms, because we understand this equality very, very, very well, okay, you, on the other hand, are still learning, which means when you see capital M, write it as the moles per liter. Okay, that should be your immediate first step. If you don't do that, you will have trouble doing your conversions later on. Okay, so please use that advice to ensure that you can do your conversions. Speaking of which, we've got some conversions. So, what is the molarity of a solution containing 24.0 grams of sodium hydroxide in 1.1 liters of solution? Okay, so again, what are we aiming for? Being asked to solve for molarity, which would be capital M, which we just said, oh my God, don't write capital M, write moles over liters. Moles of what? Okay, well, in this case, we're dissolving sodium hydroxide, so we'll say moles of sodium hydroxide over liters of what? The liters of our solution. Okay, so if that's what I want for a final answer, I now need to come up with a way to organize all of the given information so that I can figure out what numbers need to go in front of this. Okay, so let's go back and look at the rest of the given information. I have 24.0 grams of sodium hydroxide, and I have 0.1 liters of solution. Okay, so let's see how far you can get. So again, I'm going to recommend a pause here. We've got all our basic pieces put out there. Let's see what you can come up with. Yep, please do it. That would be the space bar. Okay, so now how do we go through and set this up? So we need to introduce some of that given information. My argument would probably be to introduce the liters of solution. In my answer, that liters of solution needs to show up in the denominator, so I'm going to put liters of solution in the denominator. Since I know a number with that, it's 0.100 liters. Really all we're saying is I want to place that given piece of information in the denominator. So since this is a single piece of given information, I'm going to put a 1 there. This is one piece. Okay, I don't want to put anything in the numerator because now I'm adding another piece of information. So one piece, and this was given. Okay, so that's cool. That starts to set me up on the correct path. The next thing is I want moles of sodium hydroxide in the numerator, right? So I can go back and look at my given information and be like, well, do I have that? No, I don't. Okay, but as a potential, I do have the grams of sodium hydroxide. So I do have that substance showing up. Okay, so I could place the grams of sodium hydroxide in the numerator because it's the substance, and the substance needs to show up in the numerator in my answer. So I'll go through and do 24.0 grams of sodium hydroxide. Again, this is a single piece of information, so I don't want to put it in any kind of fractions with anything else. We're just going to put a 1. Okay, and this was, again, given. So if we went through and solved this, we'd have grams per liter. I want moles per liter, so that means for sure I need another conversion. In that conversion, I need moles of sodium hydroxide. Okay, I also know that I do not want grams of sodium hydroxide. So I could place the grams of sodium hydroxide in the denominator such that it would cancel. So now I have a conversion factor that I would need to recognize that I need to have. So does this thing exist? Do I have a relationship between moles and mass? If I do, where is it found? It does exist. It's found on the periodic table. Sodium has a mass of 23, ballpark. Oxygen has a mass of 16. Hydrogen has a mass of 1. I could now add all of that up, and I would get 40, okay, grams per mole. I could now insert the numbers into this. This is 40 grams, and that is 1 mole. When I now go through and look at the unit work, it's all established and aligned such that I could go through and now enter this into a calculator, and hopefully what we would get after we did all of that would be 6. Okay, so your calculator should spit out the number 6. And we could call this 6 moles of sodium hydroxide per liter, or we could write it as 6 capital M. Okay? Just to be extra irritating, because you know that's just the way life rolls, we should evaluate sig figs. When we look at our given information, we're supposed to be reporting to 3 sig figs, so 6 molar is technically wrong, and it should be written as 6.00 capital M molar sodium hydroxide. Okay? So hopefully that makes sense, which means you should now be able to go through and solve this next one. Okay? Again, I'm going to recommend the pause, and what I'm going to tell you right now is I'm going to pause the video and actually draw in all of the work, so you're not going to get a big talk through on this. So please spend some time to actually try and get it figured out on your own first. Pause the video. So here's a bunch of stuff that I would have gone through and done to highlight where I'm going and establishing it. And then again, we should be able to work forward from this. Ta-da! So there's all of the work. Note we've identified where that information is coming from and how we got it. Notice that the placement of each of those things has to do starting from that very first piece of given information on the right-hand side. Remember, we worked right to left, not left to right. Okay? So the moles, the K2Cr2O7 was placed in the numerator because our substance is in the numerator. Okay? And that establishes this conversion and it allows us to work with it. We've now done 2 different kind of conversions with molarity. You're now responsible for digging into it and trying to figure them all out and start getting that practice. You need that practice, okay? Largely because you need the practice with the actual conversion process, and now you also need the practice recognizing where to find that information and how to pull it in and get that detail. Okay. Where this is ultimately going to go is into a much more difficult situation. Okay, and so don't worry about this Teams of thing at the bottom here, and we'll get rid of that internet meme. But we've got a big text box here, so go ahead and spend the time to go through and read it. I'll actually let the video run while you read this. So in theory, hopefully my typing and underlining was not overwhelming. I went through and underlined bits of information that I pulled out as being useful for going through and solving this. So we have 2 bits of information about our acid, and we have 2 bits of information about the barium hydroxide. Okay. Interestingly enough there, you're seeing some extra information being given to you as I write this down. Okay. One of the critical pieces to note is that we have to know what these substances are. So to even attempt to solve this question, you have to have nomenclature handy. So it is a much more advanced and challenging question, because what I'm asking you to do is think about those pieces. Okay? When it comes to an exam, I would not ask this level of difficulty of question because of the sheer volume of things that you need to be able to process to go through and do it. So when you get it wrong, I have no idea why you got it wrong. It could have been the English language. It could have been that you didn't deal with molarity right. It could have been you didn't understand volumes. There's so many different places that this particular question could go wrong that it's a very difficult question to ask on an exam. Okay? The last bit of information that you would need to go through and solve this question is the relationship between barium hydroxide and nitric acid. We said that this was that we're in a chemistry class, which means a chemical reaction makes a heck of a lot of sense to be looking at. So if you're seeing a question that lists multiple substances, writing down a chemical equation, if it hasn't been provided to you, is an excellent first step. When we write down those two pieces, we then have to be able to decide what kind of chemical reaction is this. Okay? Hopefully what you recognize is this is an acid-base reaction, and we're looking at doing a neutralization of the acid with the base, which means we're going to produce water and a salt, which is effectively a double replacement. Okay, once we have predicted our products, we also need to ensure that we've predicted the products correctly. Barium is a +2, nitrate's a -1. We did not do it correctly. Now we put the 2 in, and now we've got a proper equation. Once we have the proper equation, we can now go to balance the entire equation, and we should note that we will need to add a 2 in front of the nitric acid and a 2 in front of the water, and we now have a balanced equation. You now have all of the given information. All of this information was stashed within that sentence or sequence of sentences, that paragraph. You are responsible for needling all of that out and coming up with an interpretation for it. Okay? Now you have to go through and organize this material in such a way that you can go through and solve. That organization process should be through dimensional analysis. If you want to do it in another fashion, that is entirely your prerogative. Okay? All I'm telling you is that other fashion will very likely result in you getting the question wrong. Not because I'm being mean, but because you're going to lose track of where those pieces are. Okay? And this question is kind of neat, and I thought I had listed out all the individual steps that you would need to go through to answer this. So we're going to advance through some kind of nonsense stuff that you don't need to worry about. Okay, so this is that nonsense. And apparently I did not summarize everything for you on this. Okay, so I apologize for that. I will try and organize a slide because there's a similar example later in the slideshow or in the unit that explains all of the individual pieces that you would have to go through and solve a question like this. Okay, so with that, I'm going to go ahead and stop this video because as you saw as I advanced the slides, the very next topic we're moving into is now gases.